So now we start talking about a logical system that actually can store some data, one bit of data. And in other words, it has a state. It can be in one state or another state, and that is called a flip-flop. And this is one way of constructing a flip-flop out of NOR gates. These are NOR gates. And I take this whole circuit and I can put it in a box and I'll draw it like this. Flip-flops are often drawn with a box. You have two inputs and a state of the output given both its state and the of that state. So the fact that I use NOR gates here implies that the Q and the Q bar are always going to be complementary. If one is 0, the other one is 1. If the other one is 1, this one is 0. And you can see that if Q is 1, then the OR here is set, and the NOT makes this sure that whatever this is, this has to be the opposite of it. So let's go through the truth table of this. We have an extra line of the extra input to the truth table because the current state of the system will affect what happens when we put in various inputs. So I'm going to assume Q here, Q bar will always be the opposite, and so there's really only one extra bit of information. So I'll first consider what happens when both S and R are 0 in the two states. And we can just follow what goes through there. So this is 0 and that is 0. So if we're in the state Q equals 1, then this output is a 1. So I have a 0 and a 1, which turns on the OR, but it's turned off, so we have Q bar coming out. 0, that's 0, R is 0, and so this OR is not satisfied, so it would be 0, but it's turned on by the NOT, and so we get Q equal 1 coming out, and so that's what we have on those two rows. And you see that we start with Q equals 1, we end with Q equals 1, and so the system is stable in this, and all the feedback that we have doesn't change anything over time. So to the next state, what happens when we turn S, when S is brought high, it's a 1, and R is kept low? Let's imagine we're in the state where Q equals 1, so we have 1 and 1 here, so this is still true, and turned off by that, so Q bar is 0, so there's Q bar, 0, and then we follow Q bar is 0, comes around here, this is 0, this is off, turned on, Q is 1. So it doesn't matter whether Q bar was 0 to begin with. When we put the set on, this will come around and turn this off, and this will come on. So we will turn it on, and no matter what our starting condition is, we get Q bar equals 1 on the output. That's because S here makes this Q bar 0 and this Q 1 independent of what the state was. Likewise, if we turn off this and turn this one on, we flip the state. It's instead of no matter what it being, we turn it on. No matter what it is, we turn it off. Just because R here is associated with turning this off, rather than S here turning Q bar off. In other words, turning Q on. So finally, what happens if they're both on? Well, we can work our way through it. So S is on, and so this is on. This is off. This comes into off here. And so you would think that Q would be 0, or Q would be 1, but remember that R is also on, so this one is turning on as well. So this is on and that's off. This is trying to turn it off. And so what happens is that which one of these is on flops back and forth as fast as the signals can propagate through this one at a time. And in other words, when we stop, it's going to be in some arbitrary states. Either, whether we looked at it when this one was 1 or this one was 0, we don't know what it's going to be. The state is undefined. So we can't both have both S and R true at the same time. It's not a well-defined state. But if either one of them is not true, then it is it's fine. By the way, S stands for set. When we make set high, we know Q will be set. When we reset it, R is for reset, we know that we're going to set Q back to 0. So it's often useful to separate the S and the R from, and only allow them to change at a given time. And so we put in a gate here, and we don't allow it in. Notice I've drawn the flip-flop part here different. I've used NAND gates rather than NOR gates. I do that because now instead of S coming in, I'm going to have S bar. So if the clock is true and S is true, then I can get my signal in, but I flipped it over, so it's an S bar, not an S, that comes through, and that will now set Q. Notice Q is on top in this configuration. The fact that I've done that means I've added an extra input here to this, and if my gate is a regular signal coming every so often at a regular frequency, I call it a clock. CLK is short for clock. That's the same clock as you have on your tester boards in the lab. So we can see what happens. Here's the clock pulse. You see it's very regular. When the clock is high and S is high, then then Q will go positive on the next up clock part. And in particular, actually, I have a clock here which only works when the transition only happens when the clock is going high, and so it turns on. Here's my reset. I've turned off S, and it only works when the clock is going high again. So we see what happens. So I can, since I don't want to have S and R equal to 1 at the same time, I can reduce one of those, and I can always make sure that I give to R the opposite of what I give to S. That's the same as putting a not in front of the R and making the same input go to both. So if I have a 1 here, I know I'm setting and not resetting. If I have a 0 here, I know I'm resetting and not setting. We call this a D-type flip-flop. It takes the data. D is for data, and the flip-flop takes the state of the data. If data is 1, then on the clock the state is set to 1. If the data is 0, then on the clock the state is set to 0. Now, I had mentioned earlier that the clock will, some states will only take their state on the clock. Let's see what happens if we don't, and what we're going to have is a little bit of feedback in our D-type flip-flop. So here I'm taking Q bar and putting it into D, and what I expect to happen is on every clock cycle, I expect D to take on the opposite of what the state was previously. So if my state was 0, then I put out a 1 here, and I'll take 1 at the next clock cycle, and what I'd like to happen then is so here's the clock cycle. Before I was 0, and so so Q bar is 1, I take Q bar as 1, and I turn Q to 1. And then on the next clock pulse, I have a 0 here, so I bring the clock to I bring the state to 0. And so you see that I've divided the clock pulse by 2. That's not really what happens. What happens is whenever the clock is on, my gate is open, and I can change back and forth as quickly as the signals can go around this loop, and I don't want that to happen. So why I require it only to work when the clock is changing states on the upward tick of the clock. This little triangle there on the clock means it only changes on the upward going edge condition. That's wildly oscillating condition we had before we call race conditions, and an edge trigger prevents that. I only want to change on this upward going edge of the clock that comes in, and then I do get this behavior coming out. So a D-type flip-flop with an edge trigger on the clock, and I connect Q bar into D, will give me dividing the clock frequency by 2. Now I can add feedback both ways, and I'll get what's called the JK flip-flop. So notice here, so I've taken my SR flip-flop, and I combine the Q bar, I bring it into S, but I combine it with another input called J. So if Q bar and J are true, then I set it. if Q is true and K is true, then I reset it. In this particular case, because I have ands here, I know that both S and R can't be set at the same time, because I know Q and Q bar cannot be, they always have to be in opposite states. So I take this whole thing and I call it a JK flip-flop, and we'll talk more about that as we go along here. So here's the truth table for the JK flip-flop, and I go from, here's the state at the beginning, and here's the state at the end. So if I'm in a state equals 1, and I have both J and K equal 0, so Q is 1, K is 0, so this is 0, Q bar is 1, J is 0, so this is 0, and so I have 0, 0 here. I remain in the same state. Now if I'm in the state 1 and I set K equal to 0, then I have 1 here, and I hit the reset, and I have to go to 0. So if I have K equals 1 and state 0, sorry, I said state 0, then, no, I have state 1, and I set K equal to 1, then I know I'm resetting, and the new state will be 0. Likewise, if Q is 0, Q bar is 1, then the J works, and I'm setting it. So if Q bar was 1, I change the state with J equals 1, and that is shown 0, J equals 1, and that's here. Notice that the state here determines which of those I select, and so I only care about J when Q bar is 1 or Q is 0. I only care about K when Q is 1. And so really what happens when Q is 1, J doesn't matter. I can collapse the whole thing and just put it in it doesn't matter, and make my truth table much smaller therefore. I can rearrange this, bring the Q column over by the output column by the input column, and ask not what happens with J's and K's, but how do I go from one state to the next. So so that's called an excitation table. And for the JK flip-flop, this is everything you really need to know about it. If it's in a state 0 and you want to stay in that state, you have to have J equal 0 and K doesn't matter. If it's in the state 0 and you want to go to the state 1, you want to set it, then J is 1. It doesn't matter what K is. Again, it doesn't matter what K is as long as the state's 0. However, if it's in a state 1 and I want to reset it, then K has to be, sorry, if it's a state 1 and I want to stay in that state, then K is 0. In other words, K matters, and when it's 0, I don't change the state. When I do want to change the state, then K is 1. So two ways, again, to state a JK flip-flop. If Q is 0, then K doesn't matter. If Q is 1, then J doesn't matter. If I want to change the state, whichever J and K matters, if I want to change the state, I want to put a 1 in there. So make it turn on, J is 1. Make it turn off, K is 1.